Have you ever wondered why some reactions happen easily while others take hours, days, or even years? What controls the speed of chemical reaction? Today we are diving deep into chemical kinetics. Stay tuned till the end for numerical problem that makes this concept crystal clear. Chemical kinetics is a branch of science that deals with the rate of chemical reaction, the factor affecting the rate, and the mechanism of reaction occur. Example, rusting of iron is slow reaction while an explosion is extremely fast. Second is rate of reaction. The rate of reaction is defined as the change in concentration of reactant or product per unit time. That is, rate equals change in concentration divided by time taken. The decrease in the concentration of reactants as the time proceeds and the increase in the concentration of product as the time proceeds. Average rate of reaction equals negative of dA by dt, while instantaneous rate equals limit del t equals 0 del A by del t. We are seeing that reactant with respect to time is decreasing, that's why negative change in concentration of reactants equals positive change in concentration of product. Now the equivalent rate expression is the rate of reaction in terms of all species made equivalent. Stand about order and molecularity. Order is the total number of power of concentration variables which affect the rate of chemical reaction. It can be either integer, fraction and zero, whereas the molecularity is the total number of chemical species involved in the reaction. Order is experimental parameter, molecularity is theoretical parameter. For example, for these two reaction, it is first order bimolecular. What does pseudo-unimolar reaction means? When two reactants are present, but the rate only depends upon the concentration of one reactant, it is said to be pseudo-unimolar reaction. The example of pseudo-unimolar reaction might be the hydrolysis of cane sugar. This reaction is only dependent upon the concentration of cane sugar, not on the concentration of water, that's why it is pseudo-unimolar reaction. Type of reaction on the basis of molecularity is unimolar and bimolar. That is, if a reaction has molecularity 1, it is said to be unimolecular. For example, decomposition of O2F, and bimolecular are those type of chemical reaction which has molecularity 2. For example, dissociation of AHI. Rate constant. The rate of reaction when concentration of each reactant is taken as unity is said to be rate of reaction. Its unit is mole raised to power 1 minus m and liter raised to the power m minus 1 per second. The integrated rate equation can be given as same this one, where rate equals k times of a raised to power m. Now, if a reactant A gives product B, time t equals 0, A is present where product has not formed, that's why 0 moles of product is there. At times t equals to t, x moles of B is produced, that's why A minus x mole of A is remained. For zeroth order reaction, m equals 0 as it is zeroth order reaction. That means k in multiply by a raised to power 0 equals negative of dA divided by dt. That's why we get k equals negative of dA minus x as the concentration has changed to a minus x divided by dt. That's why by solving this equation we get x equals k times t. The half-life of zeroth order reaction is T half equals A divided by 2K. The unit of zeroth order reaction is just substitute m equals 0 in this unit. Now the example of zeroth order reaction will be reaction of S2NCl2, decomposition of N2O over platinum surface. The definition of zeroth order reaction is reaction whose rate is independent of the concentration of reactant. Its rate does not depend upon the concentration of initial reactant present. For the first order reaction, m equals 1, that is k a raised to power 1 equals negative of dA by dt. That means k times of a minus x equals negative of d by dt a minus x. If we just rearrange and integrate it, we get kt equals ln of a divided by a minus x, that is kt equals ln of initial concentration upon initial concentration minus concentration of product form. That's why T half equals 0.693 divided by k. The unit of k is per second. First order reaction, K is independent of initial concentration. The example of first order reaction could be inversion of cane sugar, decomposition of sulfuryl chloride. We discussed earlier, there are many factors that affect the rate of reaction. Let's study about some of them. Nature of reaction or reactant. If the chemical reaction is ionic, it is fast, and if the chemical reaction is organic, it is slow due to effective collision. If concentration of reactant is more, rate will also be the more. As we increase the surface area, rate also increases. Catalysts may decrease or increase the rate of reaction by alternating the activation energy. The rate of reaction doubled with every 10 degrees centigrade rise in temperature. Now, collision theory, it is only applicable for bimolecular reaction. First, let's understand about two terms, that is threshold energy. The minimum energy required before a reaction to proceed is said to be minimum energy. Activation energy is an additional energy that reactant molecule acquire over their average energy. Now, threshold energy equals activation energy plus average energy. Arrhenius equation. What is Arrhenius equation mean? ln of K1 by K2 equals EA divided by R1 upon T2 minus T1. This is Arrhenius equation. The limitation of a collision theory is it is strictly applicable only for gaseous reaction, and the molecules aren't the perfectly spare as it assumes. The energy profile diagram of exothermic and endothermic reaction is this one. You can just understand by yourself. Now there are example of a nth order reaction. Example of 0th order reaction is decomposition of N2O over a hot platinum surface. Example of first order reaction is hydrolysis of ester in acidic medium, inversion of sucrose, reaction of ethyl alcohol and acetic anhydride, conversion of N-chloroacetamide to p-chloroacetanilide. Now here are some short tricks that you can follow, that is rate of reaction decreases as the reaction proceeds. The key is called to be rate constant or velocity constant. Rate constant is temperature dependent. Molecularity does not affect the rate of reaction while order does. For exothermic reaction, EA equals del H. Catalyst shortens the time to reach equilibrium. In quantity and chemical composition, it remains unchanged. Half-life for nth order reaction is T half equals concentration divided by A raised to power n minus 1, where A is the initial concentration and n is the order of reaction. For an endothermic reaction, minimum value of EA is EA equals del H. Generally, EA is greater for del H for endothermic reaction. In hydrolysis of ethyl acetate, acetic acid acts as autocatalyst. Unit of K equals mole raised to power 1 minus 1, liter raised to power m minus 1 and per second. Rusting of iron is slow reaction, whereas explosion is fast reaction. Collision theory is only applicable for bimolecular reaction. So wrap on chemical kinetics. We covered rate law, order versus molecularity, collision theory and solved some numerical. If this is helped, don't forget to like, share and comment your doubts. See you in the next one.